Okay, thank you. It's a pleasure and an honor to be here, and I would like to thank the organizers for this invitation. Okay, so this is not a new topic, time in quantum mechanics, but I hope that I will give some, hopefully, new information and results on this topic. Yeah. So, when you ask what is behind the symmetry between space and time in quantum mechanics, you get some automatic answers, like those ones. Lack of Lorentz covariance, and X is an operator, T is a parameter, right? I will not address this because I will keep in the framework of non-relativistic quantum mechanics, but I will address this point, okay? So we will not assume that X is an operator and T is a parameter. We will assume that T can be an operator in a certain sense. But particularly, I would like to address the role of time in Born's rule, okay? So I would like to start with an evaluation of what textbooks say about this point, right? And it's quite fun. So, starting with the book by David Bohm. Okay, so you have P of x dx, the probability that a particle can be found between x and x plus dx. Okay, this is page 81, so no mention to time. But then two pages after, you get something like this, right? And like this. So time is there, but nobody speaks about it. You have a derivative, so. Where is time in the postulate that in the book of Cohen-Tanouji? It's here. When? Okay? And so on. Something similar happens here immediately after. Okay? And here it is interesting. This is a relatively new book, and we will ignore for now time dependence of psi and return to it when we discuss Schrödinger equation. But then it is too late, okay? And so on. You have lots of books. You can see that time is in Born's postulate is treated quite tangentially. But finally you get Gazirovic's, which states explicitly what we all assume when we are addressing this postulate, is that this probability, the suggestion of Max Born, defined the probability that the particle described by the wave function may be found between x and x plus dx at time t, exactly t, okay? So, explicitly or not, we get that of course, if you face t as a parameter, you can choose it exactly. You can say to the experimentalist, okay, make a measurement at t equals to pi seconds with all figures, please. But But the experimentalists will not be able to do that. Okay, because there is something strange and uncertain in time when you do quantum mechanics in the lab. Okay. So, if this is true, how can we deal with this kind of temporal exactness of Born's rule? The only way that I could figure out was to make a not so innocent rephrasing of the postulate. So you can see these as follows. You make a lot of measurements, and then you get a histogram not only for the position, but for the detection time as well. And then once you get the histogram for the times, you go to those times that you want to evaluate, and you have a quantity. So if you can do this, you can say that this represents the probability of a particle being measured between x and x plus dx, given that the measurement occurred at t, after you have the histogram. So I will make a little rephrasing here, and a change of notation, which is not so innocent. So this will be my wave function. The probability density that you measure some position, given that the time is t. Okay? So this is not new. Back in 83, Page and Wouters have considered some similar approach. And more recently, there was this work on quantum time that also has some similarities with what I'm going to present. But they are not the same. There are some key points that are different. So, but this conditional view of time, of detection time, is not new. Is not new, okay? Well, the next ingredient is that, well, I would like to define a time operator. Okay, and this, again, this is an old problem. People have tried this a lot in the past, but okay, I can give my try. Okay, the first thing is that you must be careful with a theorem by Pauli. If you want to define a time operator such that it inhabits the same Hilbert-Schmidt space as the Hamiltonian, and if you also want that they are canonically conjugated, and that time is unobservable, you have a problem. Because you can show that you get, you consider any bounded system, and then you have this as energy levels, unbounded from below. You can prove this. So there's something here that you must relax in order to get a time operator with these desirable properties. And what you can do is to the time operator to act on a different Hilbert space. So I will not push it inside the same Hilbert-Schmidt space of H. Okay, so this is the first step. Here we have the Hilbert space of a spinless particle that we are used to, and here there is another one where I will define the time operator. For now, I'll let things as loose as this. Okay, second thing, you cannot speak of, okay, why am I talking about symmetry? This symmetry that I am referring to is the statistical symmetry. I mean, I want to treat time and position as random variables some way, somehow, okay? So if I want to do this in a as symmetric as possible way, I cannot look only to position and time. I have also to look at momentum and energy. If you want symmetry between position and time at some level, you must have symmetry between energy and momentum. So we took this very seriously. I'm sorry. So here we have our usual arena. So we have the position operator, which is associated to these bases. We have momentum, and we have the most important observable, which is the Hamiltonian. It is a function of these two and of this parameter. Okay? So, because we also have to consider the symmetry between energy and momentum, now at this side I also have energy, but I downgrade it. It is similar to P here. And what is the most important observable is the momentum as a function of time, energy, and the parameter x. So I'll call it the Hamiltonian. I will say more about this in the next slides, okay? So for the moment, this is only a construction that is as symmetric as possible and that takes into account position and time, momentum and energy, Hamiltonian and Hamiltonian, if you wish. Okay, so we have our usual detection position, because this is what x is. Linear momentum, this is the space translation operator. If you want to rigidly translate a wave function, you use this as a generator, all right? And this is the Hamiltonian, which is the time evolution operator. And time is a parameter. And here, at the other Hilbert space, you have the detection time. You have the energy operator, which is not nothing more than the time translation operator. And this guy is the Hamiltonian, which is the space evolution operator. This will become more clear. It's basically just telling you the names. And x is a parameter. And you can have this without problem, all right? And also you can define it in a way that it is Hermitian. Okay, next ingredient. Statistical inference free will. I don't care if everyone in the world is asking about the probability to get 6, given that it is green. I have the freedom to ask, what's the probability to be green once it is 6? So, I wonder if I can have the opposite kind of wave function. The probability, the amplitude probability to detect the particle between t and t plus dt, given that the detection occurred exactly at the position x. Okay, so if I can consistently define this, that will be the interpretation. Now, there is an interval in time, t plus dt, and the location is precisely defined, because in that Hilbert space on the right, x is a parameter. So it must be that in analogy to this relation here, then we must have this relation here. Okay? If I am doing things symmetrically, it couldn't be different. So here is a parameter, here is the parameter, I project into the basis, and I get the wave functions which have these different statistical interpretations. Okay, and can I have a big wave function that gives you the probability to make to find a particle between x and x plus dx and t plus dt? Well, in principle, yes. You just take the tensor product of these two space, and you have this basis, and you can have this big state, which is a static, as in the Page and Wouter original paper. Right? If you want to see time evolution, you project in one of the directions. If you want to see space evolution, you project in the other Hilbert space. Okay, so as much as the momentum operator is defined by only by the differentiation rule, that small case age energy is defined as a derivative with respect to time. Okay. Next ingredient, Bayes' rule. If I want to have this, and I have this, and I have this, so I can express the probability to have A and B as a probability to have B no matter A, and the probability to have A given B, and the symmetric one. So if you extend this to probability amplitudes, we have this correspondence, and this one. Where this is a new information that gives you what's the probability that the particle is detected between t and t plus dt, no matter where. And this is the probability of the particle being detected between x and x plus dx, no matter the time. Okay? So this is the application of Bayes' rule. Okay. This is the basic formalism. But I have to show you to convince you that it may be the case that we will get some relevant information. So the first example I want to give you is something that surprised me when I first made the calculations. It's very simple. You have any bounded system, okay? So this is the Hamiltonian operator in the regular Hilbert space. You have this, and the states basically do not evolve. And the expectation value of energy is this, and there is no dispersion. Okay? You don't have dispersion in energy here. If you go to that formalism that I showed you, and, well, there is one assumption about that function f of t, which is of Markovianity. It's not essential, but it facilitates the calculation. So I am assuming that if the particle is not detected now, the probability to be detected in the next interval is the same, and then this gives you the exponential decay in the probability, right? So if you assume that, and you say that the regular wave function is one of the energy eigenstates, you can show that the expectation value of that observable in the other Hilbert space are the energy levels that you expect. However, there is a width, a uncertainty. And it is Lorentzian. So you get something like that without considering vacuum, which is possibly interesting. Okay, so you get the natural profile, which is Lorentzian. When you do consider vacuum, electromagnetic vacuum, you get Lorentzian line shapes. Okay. Well, now I will, because in the end of the talk, the final part of the talk, I will show you an experiment that we find where we were able to compare our predictions. So I will need some of this in order to make this comparison. Now, we wanted to take this, to stretch this as much as we could. So the corresponding Schrödinger equation, or mirror Schrödinger equation, is something like that. The Hamiltonian, and in that function that lives in the other Hilbert space, should be like this. And the Hamiltonian is this. Is the momentum as a function of energy, potential, and possibly time. And here, there is a fundamental thing that appears. There are two branches. If you express momentum as a function of the other guys, you get two branches. And so it is convenient to express this guy as a spinor. This means only that the particle can be detected from left and from right, or okay, whatever. But of course, in the other representation, it cannot come from past and from future. So here you have these two things, and in the ordinary Schrödinger equation, you don't. So, and the probability density would be given by this. So the equation would be expressed just formally as this spin equation, but of course it has nothing to do with spin. Okay, now you may think, I have one system. You are saying that there are two equations to describe it. This cannot be consistent. The answer is that, yes, the system is the same, but you have to tell me what is the statistical inference you want to make. Are you fixing the position of the detector, of a ideally a punctual detector, so that I fix the position, and now I record the times of the detection, or the other way around? So, yes, there are two equations, but we are talking about different experiments. The last ingredient that I need to show you the experimental results is that we indeed solved that mirror Schrödinger equation in the case of a free particle. And it is strange because you have a fractional derivative here, because it's not working well, but because of this. If the particle is free, you have the square root of a derivative. But you know that there are definitions of fractional derivatives, and then then you can solve this equation. Okay, so recall that it's a bit mind-bending because we are so used to the other representation that here stationary states are those that do not change with position. Okay, so the calculation is not that complicated, and you get this as a solution for the free particle. It is interesting because this result was already in the literature. It's so slow. So this is the probability density that comes from that solution. And for example, you can find a paper by Levens where the same expression appears. But as far as I know, all derivations have some as the one that I presented, of course, I have to step outside the traditional framework of quantum mechanics. The quantum mechanics traditional package do not allow you to calculate this kind of quantity, at least in an obvious way. Okay, so this formalism is contained in this not so new paper that we published. Eduardo Dias is one of my colleagues in Recife, and he's going for a postdoc to Oxford to work with Vlatko Vedral on variations of this problem. Okay, now the experiment. Okay, can I get some experiment and use this formalism to make predictions that are somehow useful? Probably yes. And the experiment that we chose is an old one. It's a delay time measurement. And the good thing is that we were able to extract from our theory plots of exactly the quantities that have been measured. So we could directly compare. The drawback is that this is an analogous experiment. It's not an actual tunneling experiment. It's an analogous experiment. It's a classical experiment. But given the correspondence between the Helmholtz equation and Schrödinger equation, if you do the proper assumptions, you should get the same thing. Okay, the experiment is something like that. You have a waveguide with a rectangular waveguide with a kind of bottleneck in the middle. You excite electromagnetic waves, and you have two antennas at fixed positions. And then you measure the difference in the sign, in the signal, and you have an estimation of the time that it took to traverse this region. It can be tunneling if the energy is below. It can be flight time if the energy is above. And this can be made to be completely equivalent to one-dimensional scattering by a barrier. Yes. Same object, what do you mean? Because there is only electromagnetic waves inside the waveguide. Yes, you mean that it's not a point particle, yes, but neither is the wave function. Okay, perhaps it will become more clear with the next slides. Okay, so here are the correspondence that you must consider in order to make the Schrödinger equation for this situation to be, from a mathematical formal point of view, completely equivalent to this classical situation. Okay? So what they did, they have measured the delay time, the time that took for the maximum of the electromagnetic sign to be here and from here to here, okay? And they have changed the frequency, okay? And these, the source, the microwave source that they used is very monochromatic. These frequencies are in gigahertz, and the width of the generated packet is megahertz. Okay. So here are the experimental points, and here are some quasi-classical and semi-classical expressions for the traversal time. Buttigieg-Landauer, phase time, okay? And so what have we done? We just use our time operator and we calculate its expectation value at the beginning and at the end of the barrier and take the difference. Okay? So we have a time operator which depends on the position, because the position is a parameter. I can choose. So we took the wave function, that free wave function that I have determined, because you can build it, the solution from the piecewise constant potential from that solution. And we took the difference of the expectation values. And the results are those. This is for a bottleneck of 15 centimeters. And this green result is Buttigieg-Landauer. This purple result is phase time. And the red one is hours. So if you calculate the residues, from here it's not that clear. Okay, you can say that our result is better. But if you calculate the residues, you see that indeed our result is the best one. If you take a larger bottleneck, the results are more convincing. So here it is 20 centimeters. This, at the time of the experiment, this was technically hard because there were losses and other problems. For this reason, the boxes and the bullets should coincide. They are two runs of the same experiment, but you see that there is a lot of variation here. But anyway, it's quite clear that the two other expressions are very off the target, and our result is quite reasonable. So this at least told us that we should not discard our formal structure. It's not that it is good, but we failed to prove that it is bad. And yes, because when we published that first paper, I said to my co-workers, I won't go anywhere if we do not explain some experiment. And then we came out with this tunneling thing. Okay, it's a bit early, but we have 5 minutes, so we can probably not discuss go home earlier. So we have proposed a framework which supports a more symmetric relation between space and time in non-relativist quantum mechanics. But the symmetry is not relativistic symmetry, it's just the statistical symmetry. I want to ask for histograms of space and time. I have this right, and it relies on the symmetry between x and t as statistical variables, and also you have to make this exchange between the roles of energy and momentum. And I would like to stress that it's not properly a modification of quantum mechanics, but an attempt to extend it for a wider range of statistical inference. As soon as you say that time is fixed, you get Schrödinger and quantum mechanics and regular quantum mechanics back. And we have applied the formalism to this experimental setup, and as I said, the results do not rule out the model in any trivial way. I'll finish by saying that the role of time in quantum mechanics is something that we should look at. And people, of course, understand this, and there are entire books on the topic, but not on position in quantum mechanics. So we have to look at time. Okay, thank you. Yes. I think he was first.
At one point, you mentioned the asymmetry of past and future.